This is the first of two videos that are meant to provide an introduction to hierarchical models. And Krishke, in his text, talks about mints and coins. But what I'm going to talk about are teachers and students, because to me, those are a lot more intuitive. So what we have here is a series of teachers. There's teacher 1, teacher 2, maybe teacher N, like that. And each one of those teachers has a bunch of students. So teacher 1 has this student and that student and an nth student. And what the teacher's doing is they're coaching the student. And the student is going to take some sort of standardized exam. And each student is going to have this parameter, theta, which we can think of as the skill at exam taking. So it quantifies their ability to do well on an exam. And the dependent variable is a binary dependent variable, which is y. And in this standard exam, what they're going to do is they're going to answer a bunch of multiple choice questions, and they're going to get a 1 if they get the answer correct, and a 0 if they get the answer wrong. So one of our goals is to estimate for each one of these many students the skill at taking the exam. But there's something else that's really important here, which makes this a hierarchical model, and that's the idea of, really important idea, of dependency. Because the skill of the student depends in part on the effectiveness of the teacher. And we're going to quantify that effectiveness as omega. So omega is teacher effectiveness as a coach, preparing these folks for their standardized exam. So in addition to wanting to quantify all these thetas, we're also going to want to quantify all these omegas. Okay, so now let's do just a little bit of basic algebra. And let's begin by thinking about Bayes' theorem that says the probability of theta given data, it's the posterior probability, is equal to the likelihood, the probability of data given theta, times the prior, the theta, divided by the marginal probability of the data. We've seen that many times. And now I'm going to make a couple of changes. I'm going to say, okay, instead of having just theta, now we're concerned with two things, the thetas and the omegas. So now we're interested in the joint posterior distribution of the thetas and the omegas given the data. And I'm going to get rid of this denominator, change this to a proportional sign, and say that that's going to be equal to the likelihood function, probability of the data, given the joint probabilities of theta and w times the prior for theta and w. And then what I'm going to do is, it should be a proportional, I'm going to say, okay, theta w, and I'm going to factor this out. I'm going to factor that out and say that joint probability is equal to the conditional probability of theta given omega times probability of omega. And we sort of saw that before. I mean, remember when we had tree heights and species, we said, okay, if we wanted to get the conditional probability, we take the joint probability and divide it by the marginal probability. Or we could rearrange this and say that the joint probability was equal to the conditional probability by the marginal probability. And one way to think about this is to say, okay, in order for a tree to be in a particular species and a particular height class, it first had to be in a particular height class, and then it had to be in that species given that it was in a particular height class. So what's happening here is just essentially this thing. And then what I'm going to do is I'm going to make another change. I'm going to say, okay, that's proportional to the data given theta times probability of theta given omega times the probability of omega. So what have I done here? What I've done here is essentially just forgotten about omega. And that sort of is the case. That would make sense because, once we know how skillful the student is at answering the exam, it doesn't really matter, what their teacher was. At least once after we've established what their skill is. So we can simplify this by saying once we know theta, we can kind of ignore omega. So this is kind of the key factorization that's involved in hierarchical models. And then just as a relatively small final point, let's think about joint distributions. And so earlier we saw species and height class, and in the body are joint distributions. And now we've got teachers and students, and in the body we've got joint distributions. But this is hierarchical. We've got the behavior of the students conditional upon the ability of the teacher. And so by thinking about these conditional probabilities, the conditional probability of the student's test-taking skill conditional upon the teacher's effectiveness as a coach, we can think of our model far more simply by doing it teacher by teacher instead of having to consider every possible combination of, as we showed up here, species and height. So we don't need to have to consider every possible combination of student and teacher. We can think of the ability, the skill of the student conditional upon their teacher.